So, we get to review today. Ooh. After I do series and parallel circuits, a little more. We'll do review as we go through that. Wednesday, you get your exam. Over chapters 13 and 14, and 22 and 23. The go with the flow unit. Liquids and gases moving around and charges moving through circuits. We'll be done with that. If you have not, let me put it this way, if you forgot, Friday is the last time, the deadline. In other words, you can do it anytime up until then, all semester. Your superhero paper peer review is due. Questions about that? I believe I put that as midnight, just because for symmetry. It says on WebAssign when that is. Is that what you? Yeah. So they're remembering midnight. That makes jives with what I would have thought I did. So by the end of Friday. Yeah, there's nothing you need to turn into me Friday in class. You know, you're finding someone. I sort of have to take you a little bit on the honor system with this one. Because you're finding someone to review. And then they're going to fill out the WebAssign assignment. For example, you'll fill out the WebAssign assignment for the person your paper you're reviewing. And then you'd share those comments with her so she knew it. And vice versa. And it doesn't have to be you could do it for her, but she could do it for whatever. I don't care. And you can do it more than once. You have access to the assignment. You find it's off of the scoring rubric, so you see what's what. Again, I realize this is a rough draft. It does not have to be your completed, finalized paper. However, if you don't have very much of it written, then you don't get as much feedback. Let's put it that way. So, I do realize that even if you haven't written it, you could complete the peer review and still get the points for the peer review. I realize that. But the point of the peer review is to help you have an even better paper so that your final paper, a week later on the 8th, will get the best score hopefully you can. All right? Yeah, I want to throw in too. I put it in the rubric, but where people miss the most points ultimately with the final paper is they describe lots of stuff. They describe what's happening. They're not necessarily explaining the physics. Again, yours can abide by the laws of physics or not. The whole point of the paper, the overall main point of the paper, is to get you guys to explain physics to me. I want to see if you understand things. So if you're just going through and saying, oh yes, and they jumped off the building because he's stronger than anybody. Where's the physics? Okay, how is he stronger? How does jumping off, the landing, use your fundamental physics principle and reason through it as we've been trying to in class. That's where you'll get more points. And hopefully you'll just enjoy it, make it entertaining, fun, I hope. Okay, series and parallel circuits. You guys are all poised for this. I just want to go through it. We did a series circuit at the end of last class with the Leyden jar. That was the bottle. It's a capacitor. We stored charge. It was the power supply for that circuit. Some of you might not have seen circuits drawn before. This is a typical way to do it. Here's a series circuit. Here is a power supply. Everything has a symbol, but V for voltage. So basically there's a potential difference across here. You can think of this as a battery plugging in, or the capacitor. This did work, expended energy to separate charges. So now there's an electric field established. There's a potential difference, a difference in how much energy per charge there is. When it comes out of the battery here, each charge will have lots of energy. It'll get used up by the resistors to make them light, and it'll come back in with no energy or less energy. And then it'll go back through the power source and gain energy again. But remember, these already have the charges. Review, the source of the charge is already there. As soon as you close the switch, each of these resistors, the charge is in their filaments, in the wire, everywhere, all at once, feels that electric field, the call of forward march, and they start moving. This is pushing them with the energy they need. So, let's do it. Here's one bulb. Yeah, Brenda?
I thought our book said that capacitors didn't work for series, but it could work for parallel.
They said it would, capacitor would not work for series. Do you remember why?
Yeah, the current doesn't jump.
The current. Well, let's put it this way. If you have a capacitor, you store charge. As soon as you flip the switch, you're using up that energy to light the light bulbs. And depending on how fast this discharges, capacitors usually discharge pretty quickly. Remember the one I did with the spark? That was like that. The Leyden jar, it shocked us, and it was empty. And so they're not very effective for that. They're good for short bursts, but they'd have to get charged back up or be charging and discharging. And these would start blinking, you know. So in that sense, they're not very good. A battery, the chemicals can sustain providing the push for a lot longer until you drain the battery. And then, of course, it's empty and it can't do anything. Does that help?
Yeah. I didn't understand that one part.
I'm going to have to review that myself because I don't remember what he specifically says about that. But that's my knowledge. So here's a car battery, 12 volts. Volts, that's energy per charge. So that tells us each Coulomb of charge gets 12 joules of energy. Connected up, I was the switch. And now it goes from here around to this pole, conductor, over through the light bulb, to this side, and back to the battery. So it makes a complete circuit. If I break it, disconnect it, then there's no electric field. Nothing's pushing the charges around. By the way, an electric field, they generally, the way the symbol works, this side's positive, this side's negative charges. So the electric field through the circuit is in which direction? Let you guys review. Clockwise, from the positive to the negative. It's like you got a positive plate and a negative plate, and you're hooking stuff up in between, right? The field goes away from positives because you take your positive test charge. So conventionally, when we say current, the flow of charge in a circuit, the electricity's flowing, the current, it's going this way. But that would be the positive charges. And there can be positive charge carriers, positive ions. Which way would the electrons themselves be going, which is usually what moves? Yeah, they're actually physically going the other way. The electrons would be trying to move that way. That can confuse some folks, and I find it interesting. And the way I've drawn that one, yes, counterclockwise, the electrons would be, because they're repelled from the negative side, because they're negatively charged, and they're attracted to the positive. So they go opposite the direction of the electric field established in the circuit. I thought of that while I was pointing this out. This is direct current because it's a battery, so it's always trying to push in the same direction. And they drift along. At some point, they make a full circuit. They go around, but there we go. So if you add a second bulb to this, let's make them a little smaller so it fits. What do you expect to happen if I put a second bulb in series? I heard one person say they think it'll get dimmer. Why do you think that? It's using so much current. Any other votes? Yeah.
More
More? Is there more resistance? Yeah, it has to get through two of them now. It's essentially like making a longer pipe. And that increases resistance. And from Ohm's Law, so we'll review, if you increase the resistance, Ohm's Law was this relationship. If you increase the resistance, what will happen? You see if R gets bigger? I get smaller. For the same voltage, which we have here. It's a 12-volt battery. It's pushing it with 12 volts. So if for the same push, if there's more resistance, you get less current. So we now know less current will be going through these two bulbs. Let's see. Ta-da! You're right. So in a series circuit, there's one pathway through it. There's only one way to go around. And if one lamp goes out, they all go out. You know, this one blows. It's essentially breaking the filament. And, well, you can't see both sides now. So there's no electric field established. I like old school Christmas tree lights. When one goes out, dang, they all go out. They're hooked up in series, all the ones that went out. But that also means the current, the total current coming out of the battery. So in this case, flowing through this wire out of the battery. Or disconnect it. Let go. Tighten that back up. And over here. And through here, through here, through here, through that filament, through there. It's the same current everywhere. They're all moving in sync. Because there's just one path. So in a series circuit, that's one key point I like to remember is the current's the same everywhere. But the voltage is not. It's 12 volts coming out of the battery. And that's 12 joules per coulomb. Gets here, 12 joules per coulomb, 12 joules per coulomb, 12 joules per coulomb, 12 volts. Because essentially we haven't used up any energy yet. Conductors, they have a little resistance, but very little. It's a small amount. Now the the lamp has quite a bit of resistance. So it's going to use up some of that energy per charge. And there's a voltage drop across here. The voltage here is not 12 volts anymore. What do you think it is? 6. These are identical. They have the same resistance. And so they each get half. This uses up 6 volts, 6 joules per coulomb. And this uses up the other 6. Comes back, battery does work on the charges. We go around again. So the voltages add in series. The voltage across one bulb is less than the total of the battery. But you can add them all up. They're going to be what the battery's providing. And we already talked about resistors. They just add up. Let's add a third one. And then we can make it even dimmer. So now what do you think the voltage is across each bulb? Yep, they're even more dim. 12 divided by 3 similar resistors. So yeah, they're each using up 4 volts. What if this resistor had a lot more resistance? What do you think would happen?
The last one?
This one, yeah. They'd all dim, good, because if this increases, then the overall resistance increases, and the overall current would go down. So they'd all get less flow of charge, good. And how about compare their brightnesses? If this one has the most resistance, will it be brighter or dimmer, you think, than these? Dimmer. Again, because it has more resistance. And so less current is flowing through it. Yeah, it'll be dimmer. I don't have that one for you.
So it'll be dimmer and make the other ones with less resistance dimmer too?
Overall, they'd all be dimmer. but this would be the dimmest. These two would be brighter than this if this one had the most resistance. Yeah. Let's do parallel now. Parallel, basically, they have different paths. The current can split. So you get to here, and you can go across. We've seen this. What will happen if I connect this one in parallel? That means, the current comes along, and it can go this way, or some of it can go this way. It could split. What do you think will happen to this bulb? Same? Yeah, they're both still quite bright, and much brighter than the two were in series. So in parallel, they all get the same voltage. It was the same current in series. It's the same voltage in parallel. The voltage drop, the potential difference across bulb number 1 is how many volts? 12. Look, we go from here around to here, to here, to here. And we have 12 volts here. We have 12 volts here. And this is the other side. So both bulbs see that electric field, that same potential difference of 12 volts. So in each path, they're feeling the same push. Remember, in series, you had all three. They all had to share it to get from one side to the other. But here they don't have to share the voltage. So they all get 12 volts, and more current actually flows through each bulb than when they're connected in series, which is why they're brighter. And if you undo one bulb, there's still a path to go through that one, so they don't all go out in parallel. What if I add the third one? In parallel? No guesses? They'll all dim a little, but they'll all be pretty bright in the same brightness. Is that what I heard you say? You're right. Ideally, these wouldn't dim at all. However, nothing's really ideal. And why do they actually get slightly dimmer? Because of this. They all get the same voltage, but now they have to share the current. It comes out, it's coming up here, you can think of it, and it has to split. Some goes this way, some goes this way, some goes this way. But what goes here adds to this, and that's the total that came out of the battery. When you hook things up in parallel, the battery actually has to push more charge around. More current flows out of your power source when you hook things up in parallel. So this total current is much larger for these same three light bulbs in parallel than it is in series. The battery is supplying more current because they all see the same voltage. Does that make sense? You'll drain your battery faster this way, and it'll cost more. But each bulb's brighter. Yes?
You said you're doing your battery faster this way or the other way?
This way, because it's drawing more current out of your battery. And so that chemically, this will get used up more quickly. This, from your power company too, you would pay more. You can go outside and see the little meter moving faster when you hook things up in parallel, the same things, versus series. Again, because the total current coming out is larger. Let's review the power involved. You guys remember how to find power? Work over time. Good. Good. Power is work over time. Generically, energy over time. So that's what we pay the power company for. Current times voltage is another one. Current times voltage. Because the current, review, is the flow rate of charge. And voltage is what? Yeah, energy per charge. So that's energy per time. So the power delivered to each light bulb is current times voltage. Let's look at this. In series, the total voltage is what? 12 volts. It's a 12-volt battery. And we get a certain current delivered going through every light bulb. So each light bulb uses up IV. I don't know what that is right now. My point is, though, what's the voltage parallel that each bulb sees? 12 volts, the same. For the battery. The battery's putting out 12 volts. The battery puts out 12 volts. But this current is larger in parallel. Do you see that? So there's more power being delivered to the circuit in a parallel circuit than here. That's why it drains faster. But it's a good way to review those things too. Questions? Yeah. Yes, haven't done that one yet. So here we just add up the resistors because you got to get through one before you get to the other. It's like making a longer pipe. In parallel, they split. It can go this way, or this way, or this way. It's like making the tube wider. There's more paths to get through it. What happens to the resistance? Think of water going through a pipe. If you make the pipe bigger, less resistance. It's easier to get through. It's like it can go this way, or this way, or this way. So the total resistance actually goes down. I'll put less than the total here. So the battery over there in parallel actually sees less resistance overall, which is why less resistance for the same volt, 12-volt battery, less resistance, it puts out more current. More current in a parallel circuit. If you care, you find it by doing this. 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. I won't make you calculate that, but that's how you'd figure out the total resistance there. But that's going to come out as less. So there's series and parallel circuits using all the stuff we learned in 22 and 23. So again, let's see. If you made this resistor bigger, this had more resistance than the other two, what will be the voltage across that resistor? It's still the same, because it's always the same in parallel. But how about the current change if you increase this resistance? It'll decrease. So less current will go through that one because it's harder to go through that path. Likewise, as I already asked you, if you increase this resistance, that increases the total resistance of the circuit. And so less current flows in the first place. But less current flows through all of them now. Yeah?
The parallel one, though, it wouldn't dim R2 and R2.
That's right. If you increase the resistance here, it shouldn't affect these at all. What if I just remove it? It's like infinite resistance, right? It just means no current flows that way at all. It can't. But it can still go this way, so it will. There would be less current flow, yes. Yes. Because as you remove some in parallel, the overall resistance would go back up. So there's advantages and disadvantages to both of these. But another key, in series, the current's the same everywhere. They have to share the voltage. And vice versa in parallel. The current can split, so they have to share the current. But the voltage is the same. The potential here is still 12 volts. We haven't used up any of it yet. But on this side, we're done. It's 0 volts. And so they each see that. So you can get more current. They can be brighter, but it's going to cost more because it draws more current from the battery. Total current. You can combine them too, you know, you can have all kinds of fun. But I'll just do one more. Let's say we do, this is where if you go into electronics, you know, things just get, that's the basic principle that applies to everything. It just looks more complicated. Let's do two in series. These will be in series, but they're in parallel with that one. Now I'll make you predict. What do you think will happen? These two are going to be in series, but they're in parallel with this one. Go ahead.
Well, the parallel aspect, like the one on bottom, they should both get 12, but the two on top will split 12 with 6.
Good. This one still gets 12 volts, but they have to share it. So they'll each get 6 because of the same resistance. If this was more resistance, it would use more up. Okay. Any other thoughts?
Will it overall be, will it overall be dimmer than the 3 parallels? Because this one,
Will it overall be dimmer? Do you think this one will be dimmer?
yeah, that's what I was asking. Will that one get dimmer as well, just because there is a series circuit involved in the parallel circuit?
Does this series circuit affect this path? So will this brightness change? I wouldn't expect it to either. Because we could remove this, and this can still remain lit. Other thoughts? Can you see that one? So yes, this one's still as bright as before. These are dimmer though, about half as dim, because they're sharing it. Very good. So the current's the same here as it is here, but they share the voltage. This gets all the 12 volts, so there's more current flowing there. There's more current flowing here than there is here. Because 2 resistors is more resistance for this path, less resistance in this path, because there's only 1 bulb. So there's more current flowing here than here. But these two fill the same current. You with me? All right, other questions about this electricity stuff? Got AC, DC, different. We did the current, we did Ohm's Law. Resistance, flow. Well, let's, yes?
Can you explain one more time why, so like I always thought with the parallel circuits, if you added a couple more branches that, like, that first light bulb.
Just keep adding more and more bulbs?
Yeah, but it would still stay the same, but like, I know when you, like we had 2 parallels on,
Yeah, I probably didn't.
we added one and then they all did.
You're right, I never finished that thought. Ideally, if you keep adding more and more resistors, they would all have the same brightness. However, when you do that, what happens to the current? It's going to increase. The more you add, it's going to have to supply more current. And physically, that's a load on the power source. And every time you draw more current out of here, trying to push more current, this can't keep up. And so even though it's rated as a 12-volt battery, if you measure it with each increase of load on the battery, it kind of drops. So it's just being worked harder. Which is why we saw it dim when we had 2 and added that third. They were still all equally bright, but they were slightly dimmer than before. That's because we added more of a load, which draws total overall current, which is more of a drain on the battery, and it couldn't keep up the 12 volts. It probably dropped to 11 or something, or 11.6, I don't know. So real life. If we could keep that fixed at 12 volts, they would stay the same. All right, clickers then. We'll review with some questions. Excuse me. So this one's getting at the core of electric charge will flow in a circuit when. What makes it flow? Some things can change how it flows, but what makes it flow? In other words, if you get rid of one of those answers, the charge would stop flowing. Which one is that? Has everybody had a chance? Okay, logging in? Anybody having issues? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you B. Huzzah! That's right. You got to have a potential difference. An electric potential difference. Electric potential is the same name as voltage. Voltage and electric potential are the same thing. How is electric potential different than electric potential energy?
Isn't electric potential energy like the overall electric potential energy kind of akin to potential gravitational energy?
Yeah, it's compared to gravitational potential energy. There's so much electrical potential energy. Overall, that's
But
true.
Overall, but potential and electric potential is per coulomb.
Very good. The electric potential or voltage is the electric potential energy per charge. Not overall, but per charge. And so you have to have a difference in energy per charge, voltage, potential difference, or nothing happens. You could be at 1,000,000 volts and 1,000,000 volts. You could grab that safely, as long as I wasn't touching the ground. If I was at the same potential on both sides, nothing will happen to me. Touch the ground and you're hosed. All right. Because then the ground is at 0. Now you'd have a difference. This one. All right, go. Double the voltage, what happens? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 69% of your current. That's correct. We're not done, but that's essentially just boiled down to Ohm's Law. If you double the voltage, you get twice as current for the same resistor. The resistor is what's in the circuit. So it's like taking any of these circuits and just, let's replace this with a 24-volt battery. Well, this bulb still has its same resistance, but since we have 24 volts, it can now push twice the current through it. That could blow the bulb. Actually, it probably would. Questions? Remember with Ohm's Law, you have 3 things to deal with. Generally, one stays constant while you worry about the other two. Okay. All right. What must there be to receive an electric shock? You cannot get shocked without this. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Bang. Overwhelmingly C. Good. Hallelujah. This is essentially the same question as the first one, just worded differently to throw you off. If there's no potential difference across the object, then that won't deliver any energy to those charges that are already there, and why would they want to get moving? They wouldn't. And I have one more I thought would help. All right, come on. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you think electric field. You are correct. With the author through. The electric field in a circuit travels at nearly the speed of light, not the electrons nor the current. They just kind of drift along. They're already there. They just start marching, but they can run into other things. They get accelerated. They try to go faster, but then they run into something. The electric field's what's established almost instantaneously. Questions? Yeah.
So how does electricity get to the light bulb in a constant flow?
Yeah, it's the electric field's established almost instantaneously. Series is easier to, well, actually, it doesn't even have to be series. As soon as you close the switch, here or here, electric fields are established. Or, so boom, charges here, 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 here. All feel it at the same time. Forward march. They get that push, they gain energy per charge, and they're accelerated all together. But yeah, they run into things. In DC, they eventually kind of drift, you know, they might be doing, but over time, they end up over here. And the more current that flows, the higher the current, the faster the drift velocity, and they can make it all the way around the circuit. But that's not what happens at the speed of light. Other electricity questions? I did figure most of this review would be electricity because it's the latter stuff. You've had less time to think about it. But yeah. All right, let's go 10 minutes then of the liquids and gases. And I'll start with, I have the test in my hand. But what bothers you? Did something not make sense before? Still? Well, So I want to get to that. Real briefly, what's density? Yeah, mass over volume, not voltage. Good. What's pressure? Good, yeah, it's a force, but acting over an area now. So that can change things. Very good. Yeah, if you replace the force with mg, somebody's weight in the area, and you represent the mass in terms of density with a little algebra, we did it, yeah, you end up with, where'd it go? Density times gravity times the height of the fluid, whether it's a liquid or gas. So pressure is depth dependent. It doesn't care how much you have volume-wise, just how much is above you, how deep you are. What was volume dependent? It was this one. What was volume dependent? It didn't matter how far deep you are under the water, so to speak. It mattered more about how much fluid you displaced. The buoyancy force. Yeah. So Peter goes underwater, just under the surface. He's displacing the same amount of water as if he were 10 meters underneath. So the buoyant force on him would be the same. Now, what would determine whether he sinks or floats? If the weight of what gets displaced, the fluid, is more than his weight, yeah, he'll go up. That means if the buoyant force is larger than his weight, he goes up. Vice versa, he goes down, and if they're equal, he stays put. That also we related to that in this case, this means his overall density is less than the density of the fluid around him. He would go up. These are the same condition. If his density is more than the fluid around him, he sinks. Yeah, that's all of 13 and half of 14. Bernoulli's principle, what was it? Yeah. If the fluid is moving faster, there's a corresponding drop in pressure. That sums up Bernoulli's principle. And again, that's just conservation of energy for fluids, dealing with densities and volumes. I can prove that to you again, but that's why that happens. It's just like potential energy to kinetic energy, They just kind of trade off, but the total energy stays the same. This Bernoulli's principle sums that up. So if something gets constricted, the continuity equation, it speeds up. Thus, the pressure in there will drop. Has this made you think of any questions yet? I'm going to look at my questions and see if there's something I want to make sure I'm telling you. But shout out while my head's down. So just emphasize again, pressure is depth dependent. Buoyant force is volume dependent. That helps with some of these I'm seeing already. Yep, how the buoyant force compared to the weight, that determines whether it sinks or floats. Oh, Boyles Law. Who remembers Boyles Law? It related pressure and volume. If you have a certain pressure and volume, and you increase the pressure, what happens to the volume? Yeah, it shrinks, or vice versa. That product stays the same. That's from ideal gas law. They stay constant. Example, like the weather balloon, as it goes higher and higher up in the atmosphere, what happens to the pressure on it? decreases because the pressure decreases the higher up you go. There's less air. So what happens to the balloon physically? It expands. That's Boyle's Law. What else happens as you go higher up in the atmosphere? Pressure decreases, but something else happens. Yeah, there's less air, so the density decreases too. Yeah. Do you guys weigh less when you go swimming? I know, it's kind of a trick question. I'll rephrase so it's definitive. Does your mass change? No. Do you feel lighter? Yeah, why? Yeah, there's a buoyant force helping support you. Yeah. So if I'm 160 pounds and I jump in the water, somehow I could stand on. Well, yeah, you can jump in a swimming pool. Say the water's up to here, and I'm standing on a bathroom scale on the floor in the pool. What will it read? Yeah, something less. How much less? Not an actual number, but it's represented by a term. Yeah, the weight of the water is displaced, which is the buoyant force. It should be exactly that much less. Good, Steve. Coulombs Law. The force between charges. Again, it's the same scenario with this test. You guys can have a one-page cheat sheet. You can use a calculator. There will be a makeup online afterwards again for 2 days till the Friday's lecture. For those of you that come and are actually here taking it Wednesday. But Coulombs Law, what's special about that? Yeah, it can be attraction or repulsion. And if you're a charge and I'm a charge, I'm positive, you're negative. We'll repel. We'll retract. I'm just teasing. Yeah, we'll attract. And okay, because of your charge, I feel a force. How will the force you feel compared to the force I feel? Yeah, the same. What if I triple my charge? I'm 3 pluses and you're 1 negative. What just happened to the force between us? By how much? Yeah, it increased 3 times. What if I move 3 times farther away? Ninth. It's that inverse square law. 1 over d squared. So tripling the distance doesn't cut the force by 1/3. It cuts it by 3 squared. A ninth. So that's another thing about Coulombs Law. Do you remember what polarization means? Yeah, the charges get rearranged. Yeah, it was like the balloon on the... And by the way, my balloon is still stuck to my whiteboard. I didn't touch it. It's a little lower, but it's still stuck. Any questions? We did some shielding. We did some demo on that. I asked a question. You guys had some good discussion how you can shield the radio antenna. If not, go review that one. And I did put 2 questions on there about some lamps connected in parallel versus series. They're not difficult. We covered those today. I feel good. You guys? All right. See you Wednesday.